In this paper, we present a spiking neural network navigation model, which can rapidly learn complex environments through experience. The model uses the spiking wavefront planner combined with eProp to learn propagation delays between neurons representing costs of traversal. We tested the algorithm by exploring Aldrich Park, an outdoor area in the middle of UC Irvine containing environmental features such as dirt and asphalt roads, scattered trees and grassy fields, and uneven terrain in the form of sloped hills. The robot is tasked with randomly moving between the waypoints shown on the right. While exploring, the robot uses the current drawn by the wheels, the presence of obstacles such as trees, and the slope of the ground measured by the IMU to determine how traversable it is between waypoints. In this video, the initially untrained model plans a straight path through the dense trees and sloped ground. The path is outlined in red. After around 12 hours of training, the generated cost map looks like this on the right. Nodes are colored according to cost, with high-cost areas near trees, hills, and uneven terrain. With the trained model, planning a path from the same start and end goal now produces a path which avoids the dense trees as well as sloped areas by traversing up the hill first before descending downwards. To show how our navigation algorithm continually adapts to changes in the environment, we place obstacles in the way of a path planned by the fully trained model. The location of the obstacles is marked by the star on the right. Initially, the trained robot learns to travel along the road. While traversing this path, the robot encounters the obstacles we've placed and is forced to move around them. This increases the cost of traversing between the waypoints separated by the obstacles, which our model uses to update the network weights. After a single update, the model responds to this change in the environment by planning an alternative path which circumvents the obstacles. This time, after reaching the road, the new path takes the robot up and back down the hill, avoiding both the placed obstacle as well as the existing light fixtures. We compare the spiking wavefront planner to A star, RRT star, and D star to see which algorithm is best for minimizing the cost on our cost map through real and simulated paths. In Table 1, current drawn, obstacles encountered, and slope are the costs as measured by sensors on the robot, while the normalized cost is the cost of the path through our learned cost map. We find all algorithms perform similarly, with our spiking wavefront planner accumulating less slope and normalized cost in shorter paths. To evaluate the algorithms further, we simulate paths for all possible start and end points greater than 3 waypoints apart. Our model was found to minimize the path cost through our cost map significantly better, while also planning shorter paths than RRT star, A star, and D star. The naive planner planned the shortest paths, which was expected as this planner always travels in a straight line to the goal. When looking at the differences in cost accumulated as strictly longer paths are considered, we find that the spiking wavefront planner performs increasingly better as the simulated paths become longer. To summarize, we show our model quickly generates a traversal cost map incorporating multiple forms of sensory data. Our learning rule allows for the robot to quickly adapt to changes in the environment without offline retraining. Finally, we show our spiking wavefront planner outperforms path planning algorithms such as A star and RRT star when simulating paths through our cost map. Future work plans to take advantage of our model's compatibility with low-power neuromorphic hardware.